This video see on how to analyze springback on sheet metal deformation. As you see from the screen, how the variation on sheet metal deformation as soon as a load is applied on sheet, and when you remove a load, the metal will try to return to its original shape. That's springback, one of the defects in sheet metal deformation. So as you see, this is the original deformation. When you deform a metal, initially it was this pattern. After that, when you remove the load, it tries to move backward. So that's springback. So this can be analyzed by this Abaqus software. We'll see step by step. First, we deform the metal or bend like this way. They show the first job. This one. So here is a 2D problem actually. Then you can extrude up to some depths, so we'll get some clear visualization. So for this we apply force, then when you remove this pressure, so it tries to move backward. That's springback. So let's get start. Let's show step by step procedure. So go to here, create a part that is in meter, 2D deformable shell problem, and put like 0.1 meter size, and put here workpiece. Then create this part, give dimension 0.08 and the thickness let 0.0015, that's 1.5 millimeter thickness. So put OK. Then another part, create a punch die end that of holder. So create an analytical rigid body, wire, give dimension, oh sorry, let's rewrite it, 0.04 length, and the same way 0.04. A flat radius 0.005 meter, and select the two line, click OK. So here is like let rename this one holder, and this one let rename die as bottom die. So go to here and edit the direction. So select here mirror and select this line as a mirror line and select the all entity and click done. So in the same way, copy this holder and image punch. Then go to sketch and edit similar to the previous one. So as a mirror line, select this vertical line, then select the whole entity and done. So let's add property for the workpiece still, and in general mass density, put this mesh number, then go to elastic 210 is a power of 9 and poisonous ratio 0.3, and then go to the here plasticity and plastic yield stress, put 400 the power of 6 0 420 0.6 0.02, then 500 is 0.6 0.2, and finally let's add last one 0.5 plastic strain. Okay, then select the part as a workpiece and assign the material. This section workpiece section, continue the material still and assign this, select the whole body, then okay. Then as it is in this module, in property module, let's go to die and create reference point. So go to tool, click the reference point, and this is the same way. Go select holder and tool here, reference point, last for punch, tool reference point, and select this point. Then assembly module, create instance and select all 4 parts. Okay, then go to here, translate instance, in the same way. Translate instance, select this holder. Okay, so this point and this point. Select this bottom die select this point and this point. Okay, it's properly assembled, but you must give some distance between this punch and holder equal to the thickness of the workpiece. So here let's select this one. Initial point 0.0, then move this punch to negative x direction 0.0015. Okay, here go to step. In step module we'll create two steps. One is holder force in dynamic explicit procedure. This holder force is applied on the workpiece. So put this one and put a very short period of time 0.001. In the second step, punch movement, a downward movement of this punch. So put 0.007 or 0.01 time period. So from this go to here and create amplitude. To amplitude later on we'll use this. So amplitude 1, select tabular and continue. Then time frame as 0 is 0 as 0.001 second full amplitude. So in the same way, amplitude 2 tabular at time frame frequencies at 0, we have 0 amplitude, and 0.1 second we have full amplitude. So go to interaction. So here we create two interaction property. In contact interaction, one is frictionless, and the other is with friction. So in mechanical, tangential and leave as frictionless friction formulation. So let's save it. So friction, continue here. Then mechanical, tangential, and here penalty based. Then put 0.2 friction. Click yes. Then go to here, surface to surface contact, explicit contact formulation. So before that we have done something here. In assembly we have this surface. underneath assembly we create surface. So let's punch surface, select punch. Then here one is magenta and the other is yellow color. So magenta is in contact with the workpiece. Don't miss this part. If you select yellow later on you will have a problem with contact formulation. So you must select a proper color here. So you must select here magenta color. Magenta will contact with the upper part of the workpiece. So select magenta. So in the same way, create holder surface. So in this case yellow. Click magenta. So we need two surfaces for this workpiece. Workpiece top surface, and workpiece bottom surface. Select this edge. Okay, then go to here in initial step, surface to surface, contact explicit. So in surface can select as a master surface a holder surface, and workpiece top surface. So contact here with friction. Let name this part holder to workpiece. And here select the bottom one, the bottom surface of the workpiece. Select here, then continue and contact this with friction property. And the last one, punch with workpiece top. This is like frictionless contact. So load, unload, we create a concentrated load on a punch on the first step. So here punch reference, and put much like 450,000, that means for 450 kilonewton force, and contact this with amplitude 1. So here next we got here boundary condition BC, create boundary condition. So you must create for this 3 reference points. So load, displacement, rotation, and BC die BC, they give a name for this set. And constraint in all direction. So in the same way, holder and select here holder reference, and constraint in all direction. So in the same way for this punch, create punch BC, and set this one punch reference. So constraint in all direction, and at the end we to modify this one is this punch movement. The punch will move down zero point 0.035 meter down. So contact this one with amplitude 2. Okay. So finally go to mesh and create appropriate mesh for this workpiece. Quad select this structural mesh and approximate size. We try this very coarse mesh. So let's this one 0.0005. In the material family, go to here and select this one, then select this element library as explicit and select family plane strain. Okay, then mesh, yes. So this much element size we have. You can mesh more, you can increase this mesh size, that is reduce mesh size or refine it. So let's save this part. Springback analysis side. So go to job. So here create job. Deformation. Submit the result and submit job, then see the result later. Okay, the results completed. So we have this result. So once you see the deformation or this bending simulation, our targets to see what the spring back. So I'll leave this and go to model and copy this model and say like spring back. So underneath this, delete this instance except workpiece, delete this one and set and other interaction and interaction property, delete yes. The last one, load BC in boundary condition, delete or suppress. This is similar. So go to step, delete all this, both two step, delete this, then create another step, whose name like spring back in static general and put like 0.1 time period and dissipated energy fraction with default value. Okay, then go to here, one important step here on predefined field, create predefined field and select here initial, other and initial step. So select this workpiece, so write job name. What was the job name? Deformation. Write the name of the job correctly without any error. Something spelling error means it will not work. So deformation analysis. So this one, let's check once in job, the previous job name. Okay, it is deformation. Okay, then go to job again and create job springback. Okay, then submit for analysis. See, it will take very few time as compared to the previous. Is completed. So go to result. So here is the deformed part. So go to here on time frame, this spring back, and this one is at 0, and at 1 at 0 frame it was the metal before spring back, and it is after spring back. So put this at time frame 0, then go to view, overlay, and create one layer here. The same way, slide this one up to spring back and create another layer, layer 2. Okay, then plot both layer in one, so you can see how the spring back is very small. Spring bar is this original shape. So I mean, when you deform a metal, we have this shape, but when you remove the load, it will back to try to move back to its original shape like this way. So easily you can see how the deformation looks like. So go to here and you can okay, let's here free edge. So this part one is after deformation, after spring back, and the first one is before spring back. So this is all about today's video. Subscribe, like, and share this video if you want to more video, and subscribe. Thanks for watching.